At the height of industrial ambition, engineers believed size itself could solve complex problems. The Captain, a mobile machine weighing an estimated 28 million pounds, was built to embody that belief. Designed to outperform fleets of conventional equipment, it promised unmatched power, efficiency, and control through sheer scale. Instead, it became a case study in excess, too heavy to move freely, too complex to adapt, and too costly to sustain. The Captain exposed the hard limits of engineering when ambition outpaces reality. This is the story of how a machine built to dominate its environment became trapped by it, revealing the risks of building systems so large they cannot function in the world they were meant to serve. A 28 million pound machine no one could move. The Captain was conceived as a solution to an industrial problem defined by scale, but it ultimately became a problem of scale itself. Weighing an estimated 28 million pounds, the machine was designed to function as a mobile industrial platform capable of performing work beyond the reach of conventional equipment. On paper, it promised efficiency through sheer magnitude. In reality, its size exposed the physical, logistical, and economic limits of building something so large that movement became its greatest obstacle. The idea emerged during an era when heavy industry increasingly equated size with progress. From the late 1960s to the 1980s, mega machines were seen as a way to concentrate labor, reduce operational cycles, and dominate harsh environments. The Captain followed this philosophy. Instead of coordinating fleets of smaller machines, a single colossal unit would handle tasks independently, minimizing coordination and maximizing output per operation. As development progressed, ambition drove the design beyond practical thresholds. Structural elements were thickened to handle stress. Redundancy was added to prevent catastrophic failure. Power systems expanded to meet growing demands. Each adjustment increased weight, which then required further reinforcement. This compounding effect pushed the machine's mass far beyond initial projections, locking it into a cycle where solving one problem created another. Mobility was the first capability to be compromised. Although marketed as mobile, the Captain could only move under tightly controlled conditions. Its ground pressure required specially prepared terrain, often reinforced with compacted layers designed solely for its use. Movement occurred at extremely low speeds, sometimes measured in meters per hour. Any uneven surface risked misalignment, mechanical stress, or immobilization. Relocating the machine between sites proved virtually impossible. Existing roads could not support its weight. Bridges were entirely unusable. Rail transport was out of the question. Even dismantling the machine was a massive undertaking, requiring specialized cranes, months of labor, and enormous cost. Once assembled, the Captain was effectively locked into its location, contradicting the very premise of a mobile platform. Operational use revealed additional challenges. Power consumption was extreme, often pushing local energy infrastructure to its limits. Maintenance demands were constant and intensive. Crews worked continuously just to keep systems operational, not necessarily productive. When components failed, replacements had to be custom fabricated, introducing long delays and escalating expenses. Downtime erased much of the theoretical efficiency gained through scale. By the 1980s to 1990s, the economic environment that had encouraged such megaprojects began to change. Energy costs increased. Industrial strategy shifted toward flexibility, redundancy, and modular systems. Smaller machines working in coordinated networks proved more adaptable and easier to redeploy. The Captain, optimized for a narrow set of assumptions, struggled to justify itself under these new conditions. Internal conflict followed. Engineers debated whether the machine had ever been realistically deployable. Some argued that the design had crossed known engineering limits. Project managers pointed to changing economic and regulatory conditions. Financial backers questioned whether early warning signs had been ignored during planning and review stages. Responsibility for the failure became fragmented, with no single decision clearly to blame. Safety concerns further restricted operation. The machine's own mass imposed continuous structural stress. Minor alignment errors could generate enormous forces across key components. Any serious failure risked damage not only to the machine, but to surrounding infrastructure and personnel. As a result, operating limits became increasingly conservative, reducing output and undermining the justification for its continued use. Eventually, movement slowed to a stop. The captain transitioned from an operational machine into a stationary industrial artifact. Removing it was deemed more expensive than leaving it in place. Repurposing it was impractical due to its specialized design. It remained intact, massive, and largely immobile, occupying space without fulfilling its intended role. A 28 million pound machine that could not be moved represents more than an engineering miscalculation. It illustrates a systemic failure in aligning design ambition with real-world constraints. The captain did not collapse or catastrophically fail. It simply became unusable, trapped by its own scale. In the end, the captain demonstrated that mobility is not defined by tracks, wheels, or motors alone. It is defined by infrastructure, economics, and context. When a machine exceeds all three, it ceases to be a tool and becomes an obstacle. Impressive in size, costly to maintain, and fundamentally unable to do what it was built to accomplish. Why the captain was built in the first place. The captain was not built because engineers misunderstood scale. It was built because, at the time, scale appeared to be the most rational solution available. Its creation was driven by a convergence of industrial ambition, economic pressure, institutional incentives, and technological optimism that favored singular, dominant machines over distributed systems. The logic behind it was clear, internally consistent, and widely accepted, until real-world conditions began to diverge from the assumptions that sustained it. During the late 1960s to 1980s, heavy industry increasingly equated concentration with efficiency. Large-scale extraction, processing, and earth-moving operations faced rising labor costs, stricter safety requirements, and pressure to increase output without proportionally expanding the workforce. One massive machine promised to replace fleets of smaller units, reduce coordination complexity, and deliver predictable performance under centralized control. The captain fit squarely within this industrial mindset. Another key factor was site specificity. The machine was envisioned for environments where work occurred within a confined, operational zone over many years. In such contexts, mobility appeared secondary to endurance and throughput. Designers assumed that once deployed, the captain would remain productive long enough to amortize its immense cost. The assumption was not that it would move often, but that it would not need to. Technological confidence reinforced this belief. Advances in metallurgy, structural engineering, hydraulics, and power transmission encouraged the view that previous limits could be overcome through incremental refinement. Weight, stress, and load distribution were treated as solvable engineering challenges rather than signals of systemic risk. Each problem was addressed in isolation, without forcing a reconsideration of whether the overall scale remained viable. Economic projections further justified the approach. Early planning assumed stable energy prices, long operational lifespans, and predictable regulatory conditions. Under those assumptions, a massive upfront investment appeared logical if it promised sustained output over decades. The captain was framed not as a gamble, but as a long-term capital asset whose sheer size would insulate it from inefficiency and market volatility. Institutional dynamics played a decisive role as well. Large projects generate momentum. Once feasibility studies were approved, organizations aligned themselves around the machine. Budgets were allocated, contractors invested in specialized tooling, and professional reputations became tied to the project's success. At that stage, reducing scale or canceling construction was no longer a neutral decision. It carried political, financial, and reputational consequences. There was also a competitive dimension. Heavy industry has long associated dominance with visibility. A machine of unprecedented scale functioned as a statement of capability, signaling technical authority and industrial seriousness. The captain was intended to demonstrate that its builders could operate at a level competitors could not easily replicate. This symbolic value reinforced decisions that prioritized magnitude over adaptability. Crucially, alternatives were systematically undervalued. Distributed systems of smaller machines already existed, but they were viewed as inefficient, labor-intensive, and difficult to coordinate. Managing multiple units introduced variability that planners sought to eliminate. A single machine, no matter how complex internally, promised centralized oversight, simplified logistics, and fewer points of failure, at least in theory. What planners underestimated was the cumulative cost of inflexibility. Assumptions embedded during design did not remain stable. Energy prices rose, environmental scrutiny increased, regulatory expectations tightened. Industrial strategy shifted toward modularity, redundancy, and risk dispersion. A machine optimized for a narrow operational environment found itself increasingly misaligned with the world it was meant to serve. By the time doubts became unavoidable, construction had advanced too far to reverse course easily. The question ceased to be whether the captain should be built, and became how to justify what had already been built. The project moved forward under the weight of sunk costs and institutional inertia rather than renewed strategic clarity. The captain was built because it made sense within a specific historical and industrial logic. That logic treated size as efficiency, permanence as stability, and engineering solutions as substitutes for systemic resilience. It was not irrational, it was context-dependent. In hindsight, the machine represents a moment when industrial ambition outran environmental, logistical, and economic reality. Understanding why the captain was built is not about identifying a single error. It is about recognizing how reasonable assumptions, reinforced by technology and organizational momentum, can produce outcomes that only appear flawed once the conditions that justified them no longer exist. Engineering limits pushed beyond reason. The captain did not fail because of a single design flaw. It failed because its engineering was pushed beyond the point where technical solutions could realistically compensate for scale. Every major system on the machine, structural, mechanical, electrical, and logistical, operated at the edge of what was theoretically possible, leaving no margin for error and no room for adaptation once conditions changed. The most immediate challenge was structural load. At roughly 28 million pounds, the machine imposed stresses that exceeded conventional design experience. Supporting that mass required unprecedented reinforcement of frames, joints, and load-bearing members. Steel thickness increased, internal bracing multiplied, and tolerances tightened. Each reinforcement solved a localized problem but added weight, which then required further reinforcement elsewhere. The result was a compounding cycle where engineering effort chased mass rather than controlling it. Material science offered only partial relief. Even with high-strength alloys, fatigue became unavoidable. Components were subjected not only to operational loads, but to constant stress simply from supporting their own weight. Over time, microscopic deformations accumulated, increasing the risk of cracks, misalignment, and failure. Unlike smaller machines, where parts could flex and recover, the captain operated in a regime where even minor distortion had system-wide consequences. Power transmission presented another critical limit. Moving or operating such a massive structure required enormous energy input. Motors, hydraulics, and gearing systems had to deliver sustained torque at levels rarely demanded outside fixed industrial plants. Heat buildup became a persistent problem. Cooling systems grew larger and more complex, consuming additional power and space while introducing new failure points. Efficiency losses multiplied across the system. Control systems were also strained. Coordinating the movement and operation of a machine of this scale demanded precise synchronization across numerous subsystems. Delays measured in fractions of a second translated into significant mechanical stress. Sensors and feedback mechanisms were expected to operate flawlessly in harsh industrial environments. Yet, redundancy increased complexity rather than reliability. Troubleshooting failures became slow and difficult, often requiring partial shutdowns. Mobility engineering crossed into contradiction. While marketed as mobile, the machine's ground pressure exceeded what most terrain could tolerate. Engineers attempted to distribute weight through massive tracks or load-spreading systems, But these solutions further increased mass and mechanical complexity. The machine could move, but only under narrowly defined conditions that rarely matched real-world environments. Movement became an exceptional event rather than a routine capability. Maintenance engineering faced similar constraints. Components were so large and integrated that replacing a single part could require disassembling major sections of the machine. Access points were limited. Specialized tools were mandatory. Routine maintenance tasks expanded into multi-day operations involving large crews. As a result, downtime increased dramatically, eroding the productivity gains that scale was supposed to deliver. Safety margins steadily disappeared. In conventional engineering, systems are designed with buffers to absorb unexpected loads, wear, or misuse. In the Captain, those buffers were consumed by the machine's own size. There was little excess capacity left to handle anomalies. Engineers compensated by restricting operating conditions, reducing speed, limiting movement, and imposing conservative load limits. Each restriction made the machine safer, but less useful. Economic pressures reinforced these technical compromises. Redesigning core systems to restore margins was prohibitively expensive. Scaling down was no longer an option. Instead, incremental fixes were applied to keep the machine functional, even as performance declined. Engineering shifted from optimization to containment, preventing failure rather than improving capability. Disputes emerged within engineering teams. Some argued that the machine had crossed a known threshold where complexity and scale become counterproductive. Others believed further refinement could still unlock its potential. These disagreements delayed decisive action and fragmented responsibility. No single subsystem could be blamed. The limits were systemic. Ultimately, the Captain demonstrated a fundamental principle of engineering. Beyond a certain point, adding strength does not restore viability. Systems do not fail only when parts break. They fail when constraints multiply faster than solutions. The machine was technically impressive, but it existed in a state of permanent compromise. Engineering limits were not ignored. They were challenged repeatedly, but reason was overtaken by momentum. Each successful workaround encouraged belief that the next limit could also be overcome. In the end, the machine functioned less as a tool and more as a demonstration of how far engineering could be pushed before practicality collapsed. Engineering limits, pushed beyond reason, is not a story of incompetence. It is a story of confidence carried too far, where the pursuit of scale consumed the very margins that make engineering systems resilient. The Captain did not break dramatically. It simply reached a point where no amount of technical brilliance could restore balance between ambition and reality, when scale turned into a liability. At its conception, the immense size of the Captain was presented as its greatest strength. Scale promised dominance, efficiency, and control. Larger structures could handle heavier loads, operate continuously, and replace fleets of smaller machines. Within the industrial logic of its era, size equaled capability. Yet, as the project moved from design to real-world operation, scale stopped functioning as an advantage and became the machine's most serious liability. What was meant to amplify performance instead magnified every weakness embedded in the system. The first and most visible liability was immobility. Extreme size sharply limited where the machine could operate and how it could respond to change. Infrastructure designed for conventional heavy equipment could not accommodate a 28 million pound structure. Roads, foundations, and operating surfaces all required extensive modification or complete reconstruction. Instead of adapting to its environment, the Captain required the environment to be reshaped around it. This inverted the basic principle of the industrial machinery, which is supposed to serve operations rather than dictate them. Operational flexibility disappeared as scale increased. Smaller machines can be reassigned, redeployed, or shut down with relatively minor disruption. The Captain could do none of these things easily. Once positioned, it became functionally fixed in place. If conditions shifted due to geology, market demand, regulatory pressure, or environmental constraints, the machine could not adapt. Scale transformed what was intended as permanence into vulnerability. Cost escalation followed naturally. Large machines do not fail incrementally. When a component malfunctioned, the impact rippled across the entire system. Repairs required specialized crews, custom-manufactured parts, and extended downtime. Each hour offline erased weeks of projected efficiency. Instead of lowering operational costs through consolidation, Scale concentrated risk into a single point of failure, where even minor issues became financially severe. Energy consumption emerged as another burden. The machine's massive systems demanded continuous power, often exceeding local supply capacity. Supporting infrastructure had to be expanded, adding further cost and complexity. Any interruption in power immediately translated into lost productivity. Smaller systems can stagger usage, rely on redundancy, or shut down selectively. The captain required everything to function simultaneously, leaving no margin for interruption. Scale also magnified maintenance challenges. Accessing components buried deep within the structure required partial disassembly of surrounding systems. Routine inspections expanded into major operations involving heavy equipment and long shutdowns. Preventive maintenance schedules grew longer and more intrusive. Over time, maintenance ceased to be a support function and became a dominant activity, competing directly with productive operation. Safety risks increased alongside size. Structural stresses accumulated simply from the machine existing under its own weight. Minor misalignments produced disproportionate forces across load-bearing components. Engineers responded by narrowing operating parameters, reducing speed, and imposing strict load limits. These measures preserved safety, but they also reduced usefulness. Scale demanded caution, and caution steadily eroded output. Human factors were affected as well. Operators worked within a system where mistakes carried amplified consequences. Decision-making slowed as procedures multiplied. Authority became centralized, and improvisation was discouraged. Instead of empowering crews, the machine imposed rigid constraints on human judgment. The psychological burden of managing something so large, unforgiving, and costly added another layer of operational friction. Economically, Scale locked decision-makers into a single path. Once investment reached a certain threshold, alternatives became difficult to consider, even when evidence suggested that smaller modular systems would outperform the captain. Abandoning or downsizing it was politically and financially untenable. Scale created inertia, converting flexibility into sunk cost and strategic rigidity. The broader industrial environment also evolved. By the 1980s to 1990s, industries increasingly favored redundancy, adaptability, and modular design. Systems that could fail gracefully outperformed systems that failed catastrophically. The captain belonged to an earlier philosophy that assumed stability and long-term predictability. As those assumptions eroded, Scale became a mismatch rather than an asset. In this context, Scale did not merely fail to deliver benefits, it actively prevented correction. Problems that would have been manageable at smaller sizes became entrenched. Solutions required changes so extensive that they undermined the original purpose of the machine. The very magnitude that justified its creation ultimately blocked its survival. When Scale turned into a liability, it did so quietly. There was no single collapse or dramatic failure. Instead, usefulness declined steadily as constraints multiplied. Productivity fell, costs rose, and adaptability vanished. The machine remained visually impressive, but increasingly impractical. The captain demonstrates a critical lesson of industrial engineering. Beyond a certain point, size amplifies fragility rather than strength. Scale enhances capability only when it remains aligned with infrastructure, economics, and human control. When it exceeds those boundaries, it becomes the reason a machine cannot succeed. Operational failures and mounting costs. The captain was envisioned as a machine whose immense scale would reduce operating costs through efficiency and consolidation. In reality, daily operation revealed the opposite outcome. As the machine entered sustained use, operational failures multiplied and costs rose in parallel, transforming what was meant to be a cost-saving asset into a financial drain that could not be stabilized. One of the earliest operational problems was reliability. Large, tightly integrated systems are vulnerable to cascading failure, and the captain embodied this risk. A malfunction in one subsystem rarely remained isolated. Hydraulic issues affected structural movement, electrical faults disrupted control systems, and minor alignment problems produced stress across multiple components. Each failure triggered secondary complications, expanding repair scope and downtime far beyond initial estimates. Downtime proved especially costly. Because of the machine's size, even routine failures required extensive shutdown procedures. Safety checks, depressurization, cooling cycles, and access preparation all consumed time before repairs could even begin. What might have been a short stoppage on smaller equipment became a multi-day halt. Productivity losses accumulated rapidly, undermining projected output targets. Maintenance costs escalated in parallel. The captain required continuous attention from specialized crews trained specifically for its systems. Standard maintenance teams were insufficient. Custom tools, heavy lifting equipment, and dedicated workshops became permanent operational expenses rather than occasional investments. Preventive maintenance schedules expanded, but they did not eliminate failures. They merely shifted them from unexpected breakdowns to planned stoppages that were nearly as disruptive. Replacement parts represented another major cost driver. Many components were unique to the machine and could not be sourced off the shelf. Fabrication lead times stretched from weeks to months. Inventory stockpiling tied up capital, while shortages caused prolonged inactivity. Each repair decision involved a trade-off between cost, delay, and operational risk. Energy costs further compounded the problem. Operating the captain required sustained, high-level power input regardless of output fluctuations. Even during partial operation or idle periods, energy consumption remained significant. Supporting infrastructure, generators, transmission systems, and backup capacity added additional layers of expense. Any inefficiency in operation translated directly into higher running costs. Labor expenses also exceeded expectations. Although the machine was intended to reduce workforce size, its complexity demanded highly skilled operators, engineers, safety personnel, and maintenance specialists. Staffing levels did not decline as projected. They shifted toward expertise-intensive roles with higher costs. Training requirements increased, and turnover proved expensive due to the time required to develop proficiency. As failures accumulated, operational restrictions increased. To reduce wear and risk, operating speeds were lowered, loads were limited, and usage schedules were constrained. These measures preserved safety, but reduced throughput. Lower output meant that fixed costs were spread across fewer productive hours, further increasing cost per unit of work. The machine became less economical the more cautiously it was operated. Financial projections began to unravel. Early cost models assumed high utilization rates and stable operating conditions. In practice, utilization fluctuated and rarely reached planned levels. Each unexpected shutdown invalidated previous forecasts. Attempts to recover losses by extending operating hours only increased stress and accelerated wear, feeding a cycle of degradation. Disputes emerged over responsibility. Engineering teams pointed to operational misuse. Operators blamed design limitations. Management questioned maintenance practices. Costs were debated, but no single fix could reverse the trend. The problem was not inefficiency in one area, but systemic mismatch between scale and operational reality. Over time, the machine's operating budget expanded beyond defensible limits. Keeping the captain running required continual investment with diminishing returns. Shutting it down entirely carried its own costs, but continued operation increasingly resembled loss mitigation rather than value creation. The original promise of scale-driven efficiency was no longer credible. Operational failures and mounting costs did not arrive suddenly. They accumulated gradually, disguised at first by sunk costs and optimism. Each repair, workaround, and budget revision extended viability by months rather than restoring performance. The machine remained operational, but only in the narrow sense that it could still function. In the end, the captain demonstrated that operational success depends not only on technical capability, but on sustainable cost structure. When failures become routine and costs rise faster than output, scale ceases to justify itself. What remains is a machine that works, but no longer works economically, a distinction that ultimately defines failure in industrial systems. Corporate disputes, delays, and blame. As the captain moved from engineering ambition to operational reality, technical problems quickly evolved into organizational conflict. What began as a complex industrial project turned into a prolonged corporate struggle marked by disputes, delays, and shifting blame. The machine's failures were not confined to steel and hydraulics. They spread into boardrooms, contracts, and institutional relationships, compounding the original problems and slowing any meaningful response. At the center of the conflict was responsibility. The captain was the product of multiple stakeholders: designers, manufacturers, contractors, operators, and financiers. Each party had defined roles on paper, but the machine's unprecedented scale blurred those boundaries. When failures occurred, it was rarely clear whether the cause lay in design assumptions, manufacturing tolerances, operational procedures, or unrealistic performance expectations. This ambiguity created fertile ground for dispute. Delays became the first visible symptom. Construction milestones slipped as technical challenges multiplied. Each delay triggered contractual renegotiations, cost overruns, and revised schedules. Contractors argued that design changes forced rework. Designers claimed modifications were necessary due to unforeseen constraints. Operators complained that the machine was delivered without sufficient testing. Every delay hardened positions rather than resolving them. Cost overruns intensified tensions. As budgets expanded beyond initial projections, financial backers demanded explanations. Engineering teams defended their decisions as technically sound under original assumptions. Management emphasized external factors such as regulatory changes or energy costs. Instead of unified problem-solving, discussions increasingly focused on liability and justification. The machine became a financial burden long before it proved itself operationally. Disputes over performance guarantees further complicated matters. Contracts often included benchmarks tied to output, reliability, and operating costs. When the captain failed to meet these targets, penalties and claims followed. Manufacturers argued that the machine was being operated outside optimal parameters. Operators countered that those parameters were unrealistic for real-world conditions. Legal language replaced technical language, slowing corrective action. Internal corporate dynamics worsened the situation. Different divisions within the same organization held competing incentives. Engineering departments prioritized protecting design credibility. Operations focused on reducing downtime and risk. Finance demanded cost containment. These priorities clashed, leading to fragmented decision-making. No single authority could impose a decisive course correction without triggering resistance elsewhere. Delays also carried reputational consequences. The captain had been publicly framed as a flagship project, symbolizing technical leadership and industrial capability. As timelines slipped and costs rose, executives became reluctant to acknowledge problems openly. Admitting failure risked damaging credibility with investors, regulators, and partners. As a result, issues were often reframed as temporary setbacks rather than structural flaws, prolonging unrealistic expectations. Blame gradually replaced accountability. When failures occurred, investigations focused on identifying fault rather than understanding systemic causes. Engineers blamed operators for misuse. Operators blamed maintenance standards. Maintenance teams cited inadequate access and design constraints. Each explanation contained some truth, but none addressed the underlying mismatch between scale and practicality. The search for a single culprit obscured the collective nature of the failure. Decision paralysis followed. Major changes required consensus across multiple stakeholders, each wary of accepting responsibility for costly modifications. Incremental fixes were approved because they spread risk and avoided decisive admission of error. These fixes delayed reckoning but did not restore performance. Time passed, costs accumulated, and confidence eroded. Legal considerations further slowed progress. Contractual disputes discouraged experimentation, as any deviation from original specifications risked triggering additional claims. Engineers became cautious, operators defensive, and managers risk-averse. Innovation gave way to procedural compliance. The machine continued operating in a constrained, suboptimal state because altering it carried institutional danger. By the late stages of the project, delays were no longer exceptional. They were expected. Revised schedules became routine, and cost revisions lost credibility. Stakeholders shifted focus from success to damage control. The goal was no longer to make the captain excel, but to limit financial and reputational fallout. Corporate disputes did not cause the machine's technical problems, but they ensured those problems persisted. Organizational fragmentation turned solvable challenges into entrenched failures. Without unified authority and shared accountability, corrective action arrived too late or not at all. In the end, the captain became a case study in how large-scale projects can collapse under the weight of institutional conflict. Engineering complexity strained machines. Corporate complexity strained decision-making. Delays multiplied, blame circulated, and responsibility dissolved across layers of management. What remained was a machine trapped not only by its scale, but by the organizations that built and managed it, unable to move forward, technically or institutionally. Abandonment of a machine, too big to save. The end of the captain did not come with a dramatic collapse or catastrophic failure. Instead, it arrived gradually, through a series of decisions that acknowledged an uncomfortable reality. The machine was no longer worth saving. Abandonment was not a single event, but a process shaped by cost, risk, and the recognition that recovery demanded more resources than the machine could ever justify. The first step toward abandonment was operational retreat. As failures accumulated and costs escalated, usage was quietly reduced. Operating schedules were shortened, loads were limited, and movement was minimized. Officially, these measures were described as optimization or safety precautions. In practice, they reflected a loss of confidence. The machine could still function, but only within an increasingly narrow and inefficient envelope. Maintenance soon shifted from preservation to containment. Instead of restoring full capability, crews focused on preventing catastrophic failure. Temporary fixes replaced comprehensive repairs. Components were reinforced rather than replaced. Systems were bypassed rather than redesigned. Each intervention extended survival by months rather than improving performance. The goal was no longer recovery, but avoidance of collapse. Financial reality accelerated this shift. Comprehensive refurbishment would have required dismantling major sections of the machine, fabricating new components, and reinforcing supporting infrastructure. The projected cost approached or exceeded the expense of building smaller, more flexible alternatives from scratch. Investment committees faced a clear comparison: spend heavily to revive a flawed system or redirect resources toward solutions with lower risk and higher adaptability. Logistics made abandonment even more likely. Removing the captain from its site was impractical. Its size exceeded the capacity of roads, cranes, and transport systems. Disassembly posed its own risks, including structural instability and environmental damage. The safest and cheapest option was often to leave the machine where it stood. Immobility, once framed as manageable, became final. Organizational incentives reinforced inaction. No department wanted ownership of the decision to dismantle or decommission the machine. Abandonment implied admission of failure, with political and reputational consequences. As a result, responsibility diffused across committees and agencies. Delays were tolerated because they postponed accountability. Over time, operational knowledge eroded. Experienced crews were reassigned or left. Training programs were discontinued. Documentation became outdated. As human expertise declined, restarting or restoring the machine became even less feasible. The machine was still present, but the system required to operate it was quietly dissolving. Environmental and safety considerations further constrained options. Aging structures accumulated stress, corrosion, fatigue, and misalignment increased risk. Any major intervention carried the possibility of uncontrolled failure. Risk assessments increasingly favored leaving the machine untouched rather than attempting ambitious repairs. Stability became synonymous with inactivity. The machine's symbolic value also changed. What was once presented as a triumph of engineering became an embarrassment. Public references diminished. Reports emphasized external factors rather than internal decisions. The machine remained physically dominant but institutionally invisible, existing outside normal operational planning. Eventually, abandonment became the default state. Power systems were shut down except when necessary. Maintenance was reduced to monitoring. The machine transitioned from asset to liability, occupying space without contributing value. Its continued existence was justified only by the cost and risk of removal. Abandonment did not mean total neglect. Surveillance, safety checks, and minimal upkeep continued to prevent environmental or structural hazards, but these efforts served containment, not recovery. The machine was preserved as an inert structure, not as a functional tool. The captain was too big to save because saving it required reversing every decision that created it. Scale could not be reduced. Infrastructure could not be easily rebuilt. Economic assumptions could not be restored. What remained was a machine perfectly adapted to a past context that no longer existed. In the end, abandonment was the most rational outcome available. It acknowledged limits that engineering, finance, and institutions could not overcome. The machine did not fail because it stopped working. It failed because continuing to work on it no longer made sense. Abandonment transformed the captain into a monument to excess capacity and constrained choice. Not destroyed, not dismantled, but left behind, it marked the point where ambition exceeded correction. Too large to move, too costly to fix, and too risky to revive, the machine remained where it stood, silent proof that some systems do not end with failure, but with resignation. The problem of building what cannot be used. The captain ultimately exposed a problem that extends far beyond a single machine. The danger of building systems whose scale, complexity, and assumptions render them unusable in real-world conditions. The machine was not unfinished, nor was it poorly constructed. It was completed largely as designed and performed many of its intended functions. Yet completion did not equal usability. This gap between technical success and practical failure defines the core problem that sealed its fate. At the heart of the issue lies a misunderstanding of usefulness. Engineering success is often measured in terms of feasibility. Can something be built, powered, and made to function under controlled conditions? Usefulness, however, is contextual. A machine must operate within economic limits, infrastructure constraints, human systems, and environments that evolve over time. The captain satisfied feasibility while violating usability, demonstrating how easily the two can diverge when scale overwhelms context. One contributing factor was extreme over-optimization for a narrow scenario. The machine was designed around specific assumptions about terrain stability, energy availability, regulatory predictability, and uninterrupted long-term operation. Within that narrow window, it could perform as intended. Outside of it, performance degraded rapidly. Systems optimized this tightly are inherently brittle. When conditions shift, adaptation requires redesign rather than adjustment. Flexibility was sacrificed to maximize output under idealized assumptions. Scale amplified this fragility dramatically. Smaller machines tolerate mismatch because they can be modified, relocated, or replaced with limited disruption. A machine weighing 28 million pounds cannot. Any miscalculation becomes permanent. Errors that would be manageable at smaller scales become embedded features at larger ones. Usefulness declines not because the machine stops working, but because it works only when circumstances align perfectly. Institutional behavior reinforced the problem. Large projects reward commitment, continuity, and persistence even when warning signs emerge. Once reputations, budgets, contracts, and authority structures become tied to a system, Acknowledging unusability becomes politically and financially difficult. Decision-makers continue investing not because the system performs well, but because abandoning it appears worse. This dynamic allowed the captain to progress far beyond the point where practical use could be realistically guaranteed. The separation between designers and operators also played a critical role. Engineers focused on achieving technical milestones, while operators confronted daily constraints. Feedback from real-world use arrived slowly and was often filtered through layers of management. By the time operational limitations became undeniable, design flexibility had disappeared. The machine was already locked into its physical and conceptual form. Economic signals failed to intervene early. Initial cost-benefit analyses relied on optimistic projections and stable assumptions. As operating costs rose and output declined, those models were revised repeatedly rather than discarded. Sunk cost logic replaced forward-looking evaluation. The guiding question shifted from, "Does this machine work?" to, "How much more must be spent to justify what has already been spent?" Usefulness also depends on reversibility. Effective systems allow disengagement when conditions change. The captain did not. Its size prevented easy shutdown, relocation, or dismantling. Every alternative carried significant cost and risk. A usable system allows exit. An unusable one traps capital, labor, and attention long after its purpose has faded. The broader lesson is not that large machines are inherently flawed. Scale can deliver value when aligned with infrastructure, adaptability, and governance. The problem arises when scale outpaces those supports. At that point, engineering success produces operational paralysis rather than capability. The captain illustrates how technological ambition can outrun practical integration. Engineers proved the machine could exist. Institutions failed to ensure it could be used sustainably. This mismatch transformed a functional object into an inert presence, occupying space without fulfilling purpose. Building what cannot be used is not an accident, it is a process. It begins with reasonable assumptions reinforced by expertise and confidence. It continues through incremental decisions that favor continuation over reconsideration. It ends when a system remains intact but irrelevant. In the final analysis, the captain was not useless because it lacked power, strength, or sophistication. It was useless because it could not fit into the world around it. Usefulness requires harmony between machine and environment, between ambition and constraint. The problem of building what cannot be used is not solved by better engineering alone. It requires restraint, feedback, and the willingness to stop before completion becomes inevitability. The captain stands as a reminder that the most impressive systems can fail not by breaking, but by existing without purpose, complete, immobile, and fundamentally unusable.